So actually, I'm not quite open to give a talk in the conference right now, but unfortunately, my student has a very complex visa issue. So then I come here to introduce this work. And actually, this work is not a mainstream of my research, but here's the mainstream of my research in my group. Actually, in my group, we have done a lot of this business analytics work. So basically, my research philosophy, since we're doing data mining, all my research is actually collaborated with industry. So we have done the work in the mobile intelligence and also B2B marketing and the business analytics like supply chain analytics. And also right now I'm doing people analytics as well as for the venture capital analytics. So, but certainly this work is along the line for the mobile analytics. As I mentioned, for this work, we collaborate with the industry. So, but it's not following the mainstream of my research. So why we come up this collaboration? So the idea is nowadays we use a lot of this mobile social messaging system, like WhatsApp, like WeChat, and Facebook. So we can see this drastically growth of all these kind of internet activities available. So what's actually happening is for all this messaging system, and now all these applications, now they change to use the secure protocol. Secure protocol make it difficult actually for us to understand the in-app all these user activities. So what do you mean by that? Say for instance, right now if you use WhatsApp or use WeChat or Facebook, people can do various different types of service. Say for instance, you can texting, you can do the video call, you can do the voice call. So we have different these service types. From the internet service provider perspective or from the many companies' perspective, they try to understand what exactly the users are doing. They don't necessarily know the content, but they want to know you are doing texting or you are doing video call. What's the motivation behind this? We try to understand all this, what actually user doing is we can help to understand user preference, and also we can help the internet service provider to provide the personalized service to the people. And also, it's better to use the network resource distribution. Say, for instance, if we know the user actually is doing video call or doing voice call, so we can provide a better quality of service from the network bottom line perspective. So we can provide a better quality service for the packet routing or those type of things. So this way, once we understand what kind of activity actually is happening in the in-app activity, we can help to improve the user experience and those type of things. So that's the key motivation behind this. So now we know the problem we're working on is we try to do this in-app activity analysis. The key objective is we try to understand mobile user, what exactly they do, what kind of service type we have. And but the problem is we had constraints, two constraints. The first constraint is now we are facing this secure protocol, right? It's unlike before. For previous case, if the traffic is not encrypted, it's very easy. We use some packet examination software, inspection software. You can exactly see the content. But now you cannot. So that's the first challenge we're facing. The second thing is the company requires us to do this thing in a real-time fashion. So in a real-time manner, this makes this, we know the challenge. Say, for instance, how much traffic going on for those Facebook and WhatsApp and also the WeChat. So how it be possible to do these things in a real-time fashion? So that's two key challenges we have to face these two problems. For the encrypted traffic, let me highlight. We only have very limited information for the encrypted traffic. Say, for instance, we only know the packet length, and also we only have the timestamp for each packet arrived. So let's, and also we know the prototype, like they use TCP or UDP, those type of things. So that's all we have. We don't have anything else. So based on those type of information, we try to do this prediction, say what kind of service actually user is doing. So I just try to give the problem picture. Here we have some definition, but it doesn't matter. So the problem scenario is we have a stream, right? If two users are doing communication, we have stream. So every packet is keep arriving, right? And this is bottom level is the very fine grained level. So it's very difficult to directly to classify, say, every packet belong to what kind of service. Say, for instance, it's very difficult to say this packet belong to texting, this packet belong to voice. It's very difficult. So actually, we doing something is we have to move up a little bit from the conceptual level. So what we propose to do is we are not exactly to classify every packet. What we try to classify is we first group the packet together somehow. Say, for instance, we group all these packets we believe they belong to the same service type and using the clustering methodology. Then we call this as a segment. So for every segment, once so it's more like we have the sequence. We first doing the cut chunk to cut them in each segment. This segment can be longer, can be smaller, as long as we believe all the packets belong to one segment, they actually from the same service type. Once we have this segment, then we build a learning model. Actually, we predict that every segment belongs to which service type. So that's pretty much the idea we have. But in order to capture this traffic segment, and we actually use the time window, the representation. So starting from the beginning of the stream, and we have the time window with a fixed size, and we actually sliding window, and for every window, we allow them to have a small overlap. So, but of course, all this window size, you will ask me, how do you specify parameter? It's difficult, trust me. We actually have many this kind of parameter from the domain knowledge. Because this, as I mentioned, this is industry project, and this actually is fully function, right? And so we will have some parameter. I admit that right now. So, and also we have some this know-how things. So that's the basic idea. We have this definition for the raw flow, and also we do this traffic segmentation, and also we do this time window representation. So how about data? We actually we have our students and also the some employees from the company. We help to develop this data collection scenario, and we actually collecting the data by ourselves. So we use different types of mobile apps like WhatsApp, Facebook, and also the WeChat. We collect the data from our volunteers. So this just gives you some indication why it's possible to actually using this very limited information to do this classification, understand that this traffic is belong to which service. So we can see, say for instance, this text information and these are moment information, which is actually the packet length and also the density they arrived. And this actually will show the audio, and this shows the picture. So you can see clearly, say, for instance, in terms of packet length, and for different usage type, they have a different length range. And also, for the moment and the text, they have different density distribution. So all this actually give us some indication. So it's possible we generate some statistical features, and actually coming out, say, for instance, can be linked to the packet length, and can be linked to the packet time. Arriving time, and also the traffic speed, and also the traffic density we have. So here we formally define our problem is, as I mentioned, we try to do this traffic classifier, and we try to understand this portion of traffic belong to what kind of service type, right? And we use this segmentation strategy. So because it's difficult to directly classify every packet, so instead, we first group the packet we believe they belong to the same segment together, and then we predict each segment. So that means we have two steps for this project. The first step, we do the traffic flow segmentation. The second one is we do the classification. And you can see this is a multi-class classification problem. Say for WeChat, we have actually 8 service types, and for the WhatsApp, we have 6 service types, and the Facebook, we have 5 service types we have. So here is the framework for the whole work. Actually, I just highlight some key things. So we have offline work and also the online work. offline work, the key here is actually we try to capture the optimal feature set. It's more linked to the feature selection. No, of course, we have data collection. And for the online analysis, is actually based on the optimal feature set, we actually identified from offline analysis, and we actually bring them to the online and to develop this prediction model. But the process is actually very simple. For all this law sequence, right, as I described, we have this time window is actually sliding window. For every sliding window, we can extract a vector of features, right? And based on all this sliding window, and we're doing some segmentation, can link some window together, so form the segment. For every segment, we believe the activity in those segment, they actually belong to the same service. And once we have all these segments, we build the learning model. On top of this segment, we predict that each segment belong to what service type. So that's the whole picture of this project. So here we show, so this I just described. So this is the whole scenario. We have the low traffic scenario, and we have this time window sequence coming, and we extract every feature vector associated to each window. And based on the feature vector we have, we can do the clustering, and we try to capture the segments, which actually we believe any packet belong to the same segment, they belong to the same service type. So this is the whole process. So for this time series way, we have this feature extraction is, in the end, we come up with a full set of 30 features. And out of these 30 features can be grouped actually into 4 types. The first group is packet length related feature. Say, for instance, so essentially it's some basic statistic of linked to the packet length. And also we have some packet time related feature. Say, for instance, can be some adjacent packet intervals and some gap skewness. And also we have the traffic packet density information, and also we have the traffic speed information. So basically we can say average packet size when they arrived. So those information can actually help to identify, say, for instance, for the video call and the voice call, those packets they come in very fast way, and the density is very high. So the problem here is we actually do the feature selection, have this complete set of 30 features, and which divide into these 4 categories. And the challenge is, as I mentioned, first, we have large volume of this low packet keep arriving in a real-time fashion. And the second way is the whole framework, as I mentioned, our approach. So there's several critical issues. The first critical issue is segmentation quality is very important, right? If, as I mentioned, for every segment, our assumption is for any packet that belong to one segment, they should belong to the same service type. So if our segmentation didn't do well, then everything is wrong, right? So that's some challenge, and also the high volume of the packet arrive. That's another challenge we have. So here comes next I'm introduce the segmentation. For the segmentation, here we first introduce the similarity measure. We try to say, for instance, how we say 2 packets. In terms of the 30 features we have, they are very similar. They suppose they should belong to the same service type. So we actually, this is more engineering. I admit that. We actually tried many different types of similarity measure. Eventually, we use this one, this Gaussian kernel. For f prime is 2 features. For every individual value, we just compare the similarity. So it's just like class validation. We have internal class similarity and intra-class similarity and the inter-class similarity. And here we define. So basic idea is for each segment, we try to maximize, for any packet within the same segment, we try to maximize their similarity. And for any packet they doesn't belong to the same segments, we try to minimize their similarity. So eventually we use this combination of objective. So intra-class, so within the class similarity minus the between-class similarity. So we try to maximize this value. So that's the our similarity objective function. So here's some result we actually have is we actually try all these 30 features. As mentioned, we're doing this feature selection. We try to identify the best feature set for this classifier build. So actually, it turns out, say, for instance, we have several curves here, and this one corresponding to this value. So we can see when this value achieves the largest value is for the future, the number of features is actually 6. So we get this optimal feature set. Actually, we have is 6 features. So for this optimal feature set, we have actually I'm listing here, and I'm not going to go over the detail for these 6 features, but you can read the paper regarding this. And once we have this above, we just showed the feature selection. The next, I'm going to introduce this clustering algorithm. This clustering algorithm, we use a very simple one, fairly simple one. It's just like k-means, but of course, we're doing some change on the k-means. We put some constraint because all this time window, right? So we put some constraint. So if for every segment, right, they just a collection of all these time window, they link them together, but they have to link them follow the time this is timestamp order. So that's the only constraint we have for this k-means clustering. But actually, we're doing things very easy. We're doing this bisecting k-means, similar to bisecting k-means. So say, for instance, if anything, this is stream, right? We cut by half, and we calculate, say, for instance, the similarity between these two. We use the objective function to use this similarity value, and we can actually cut them by half, and we check the inside. Say, for instance, we have a threshold to check. Say, the segment we have for this, say, for instance, the left half, if the threshold less than some threshold, we get from the domain. And many this kind of real-world scenario, we get this threshold. It's a parameter, but we land from the real-world scenario. If less than this threshold, that means the many packet belongs to this segment. They actually may not come from the same cluster, may not come from the same service type. We further break them into small two. So every time we just like recursively break them into two, unless we finally reach the stage, say, for instance, this is small segment. For every packet, their similarity total value is greater than some threshold. Then we see, now we find, we believe them, they belong to the same service type. So that's the basic idea we have. So in terms of real-world result, first, this is industry deployed project. So we actually have the real-time online version. They function right now. So we only use this synthetic, not synthetic, this real-world data we actually collected by our volunteer, either from the student group or from the company employee. So we collect the data for the WeChat and Facebook and also the WhatsApp. This is from 3 applications. And so here I just want to mention one thing is, for many service type, as I just mentioned, we have two service type, actually 2 types of service which are actually relatively easy to be separate. Say, for instance, video call and voice call, which actually use UDP protocol, and for the rest, they use TCP protocol. So simply based on protocol, we can separate these 2 groups. And then for no VoIP traffic, we actually we build a random forest tree, and then we try to predict every segment actually produced. So here is some benchmark methodology for the existing literature, some from communication network domain. And so the result actually, we actually compare the result in offline version and also the online version. For the offline version, you can see F measures. So this is our method, and so this we have this traffic duration accuracy and the traffic volume accuracy. So you can see this black color shows our approach. So certainly, well, of course, our method is better than the benchmark and also existing methodology right now. And also, we actually compare this offline version with WeChat, WhatsApp, and Facebook for all these three. And also, we want to show, and this actually the requirement from the company. They want to us to compare the scenario between, say, for instance, we have different means. This service type we keep coming out. Say, for instance, if we only have two service types like audio, and audio location, audio moment, and what's the performance. And also you can clearly see our approach is better for these two validation metrics as well. So this is the real-time version. For the real-time version, actually what we do is every packet, once we receive every new packet, right? And the future vector for this current will be updated. All the information in the future vector will be updated, right? And so for all this online testing version, and here we compare two things. One is the time efficiency and also the accuracy. While this approach is actually very simple, traditional sliding window from the communication domain approach they're very simple, and their efficiency is slightly higher than, is better than us, but their accuracy is extremely low. So in terms of accuracy, our approach is much better. So this is the old approach they're using in their platform, but right now they use our approach. So I think that's pretty much for my today's talk. So I just want to share some experience. As I mentioned, this work is not following the category for my mainstream of my research, but from this project, we really learned a lot. So because this is a real industry project, during this process, particularly for the, we have the stage to make this work online. So a lot of challenge. Starting from the data collection and also all this approach development and the several parameters we have to tune. So in the end, well, finally, it turns out it works. So far, at least it works well in the company. So I think that's all for today's talk. And Jimmy is my student, and actually I try to promote my student a little bit. He's very good, actually. So unfortunately, I hope he can come here to give the talk. And he from physics background, and originally doing PhD at the Rutgers physics department. And but he managed to come to my lab and spend 2 years in my lab, not my students. But eventually, I'm very happy to have him, and he's doing an excellent job. So, any question? Thank you.